This is a short lesson on adding and subtracting radical expressions. So if we look at these two examples here, first thing that we need to do is to simplify, which remember it means to take out the perfect squares. So we want to look for any factors within our square roots that are perfect squares. So the first one here, 24, we can divide by 4, so that's a factor. That is a perfect square. 28, we can also take out 4. So 4 times 7 gives us 28. So we're basically writing these in factors where one of the factors is a perfect square. For 54, we can take out 9, because 9 times 6 is a perfect square. And for 175, we can take out 25, because 25 times 7 gives us 125. So you'll notice that we have perfect squares. If you can't see, or if you don't remember what the factors are that go into these that are perfect squares, remember you can always make a factor tree to figure out those factors. So once we have those factors identified, we can take them out as the perfect squares that they are. So square root of 4 is 2, square root of 9 is 3, square root of 25 is 5. So on the outside of our radicals now, we have in each case here 2 factors, so we've got to get those together. So 7 times 2 gives us 14. 6 times, sorry, said that backwards. 3 times 2 gives us 6. 9 times 3 gives us 27. And 6 times 5 gives us 30. So we end up with these expressions. Now, so far we have done nothing that was adding and subtracting radicals. The next step is where we're actually adding and subtracting the radicals. So any radicals that are considered like radicals can be combined. So like radicals, remember, means that they have the same radical part. So 6 root 7 is a like radical to 30 root 7. And let me just grab a different color here. 14 root 6 and 27 root 6 are like radicals. So we can combine those ones together. Do pay attention to the signs. So 14, whoops, gotta get out of that highlighting. So 14 and 27 gives us 41 root 6. So notice that the root part stays the same. Just like if we were adding 14x and 27x, we'd get 41x. When we add 14 root 6 and 27 root 6, we get 41 root 6. Likewise, with the 2 I've highlighted in yellow, 6 root 7 plus 30 root 7 is going to give us 36 root 7. So there's our final answer. Guess I should circle that since it's our final answer, right? So similarly with the second one, we're going to start by taking out perfect squares. So from 112, we can take out 16. That one might be a little less obvious. So maybe we should do that one off to the side here. Right, so if we look at 112, my off to the side here is not so off to the side. 112, I'm just going to do the factor tree here. So if you can't take out anything else, one thing you can always start with is 2. Right, so 2 goes into 10 5 times, 2 goes into 12 6 times. Then we can take out another 2, and we get 2 times 28. I'm off the screen here, and I can't move over. So let me just rewrite that where we can see it. 2 and 28. And then 28, we can go 4 and 7, and the 4 we can go 2 and 2. So where our 16 is coming from, right, is my 2 times 2 times 2 times 2, and then the 7 left over. The 9's a little more easy to see from our 18, 25 from the 175, and 49 from the 98, all perfect square factors. So once we've got those perfect square factors taken out, then we can actually take them out of the radical. So square root of 16 gives us 4, square root of 9 gives us 3 on the outside, square root of 25 gives us 5 on the outside, and the square root of 49 gives us 7. Once we've taken them to the outside, we can combine them. So 4 times 2 gives us 8, 3 times 3 gives us 9, 2 times 5 gives us 10, and the 7's all by itself, so it just stays 7. So now our like terms, we've got 8 root 7 and negative 10 root 7, watch those signs. And we have negative 9 root 2 and negative 7 root 2. Again, watch those signs. Because now when we go to combine the like terms, 8 subtract 10, we're going to get negative 2 root 7. And negative 9 and negative 7 is going to give us negative 16 root 2. So again, we can identify there's our final answer. So there's our 2 examples, adding and subtracting, and we'll stop there.